So we've talked about arc length, which is a portion of the distance around the circle. So it's a portion of the circumference. Today we're going to talk about area and the area of a sector. And then we're going to go into the area of a segment, and I'll explain what all those are. But the area of a sector is a portion of the entire area, just like the arc length is a portion of the entire circumference. So first, let's talk about area is the number of square units that are contained within the interior of a figure. So where circumference is the distance around a figure, then area is the space inside. Okay, so this is circumference and this is area. The equation for the area of a circle is pi r squared. Don't get confused because circumference is 2 pi r. There's a 2, there's a pi, there's an r, but 2 times r is very different than r squared. So be sure you keep straight which one goes with which. Area is measured in square units, such as meters squared, feet squared. Feet squared can also be written square feet, yards squared, inches squared, anything squared. Okay, so the area of a sector, just like we did with arc length, we're going to do the same thing with the area of a sector. So a sector is this little piece, right? This little piece of the circle that is enclosed between the radii of a circle and the intercepted arc. So that is your sector. So when I want to know how much area, how much sauce am I going to need to cover that piece of pizza, then I take the angle theta at over 360. So just like we did before, and then I want the area of my sector. I just put a little s down there to remember that it's the sector, not the whole area, over the entire area of the circle, which is pi r squared. Now that should look very familiar to you. The only difference between this and what we did the other day is this little piece right there, because it's depending on the whole. Do I want the whole distance around, which was circumference? It was pi or theta over 360 is equal to the arc length over 2 pi r, right, over circumference, because I wanted the part of the distance around, or do I want the part of the area? Then when we get to the area of a segment is this little piece. It's the space that's enclosed behind the chord in a circle. So we have chord PQ. So it is the space that's enclosed between the arc PQ and chord PQ. And so that is our segment. Now the way that we find that is we take this sector, right, this orange sector, and we subtract away the triangle, and then that will leave us with that blue piece. So we take the area of the sector and we subtract the area of the triangle, and that's what's going to give us our segment area. Okay, so you want to take that whole piece and then you want to cut off the crust. Basically, that's what's kind of going on with this. So let's look at a couple of examples. It's going to tie together what we did previously too, because we want the area of the sector and the arc length. So I want the area of that small piece and I want the length of the arc of that small piece, RS. Okay, the actual length of the arc, not the measure of the arc. So the area of the sector is 63 degrees out of 360 degrees is equal to the area of the sector, which is what I want, the area of that shaded in piece, divided by pi r squared, 25 pi. So when you solve this, you get 63 times 25 pi divided by 360, you get 13.7 units squared. And then to find the arc length, so I just don't want you to see these side by side, it's still 63 over 360, and it is the area of the sector, so, or not the area of the sector, I'm sorry, I want the length of the segment, right? So I'll call that S, the length of the segment, or the length of that arc, divided by the entire distance all the way around, which would be 2 times pi times r. We could go find it and then come back and plug that in, but we can just do this all at the same time. So you cross multiply 63 times 10 pi divided by 360, and you get that the arc length is 5.5 units. Same thing with number 2. The only difference is I want the shaded sector, which is this big piece. Well, in order to do that, I need to know what that theta is, what that angle is. Well, if the small piece, if AOB is 60, then the flip side of that, the rest of the circle has to be 300. So the area of the sector would be 300 degrees divided by 360. is equal to the area of the sector, the area of that big piece, divided by pi times 18 squared. Now, you could find the small piece and subtract it from the whole thing. You could do that if you don't want to deal with bigger numbers. So you take 300 times 384 pi divided by 360, or excuse me, 324 pi divided by 360, and you get 848.2, and that's meters squared. In this particular case, because it's 300 degrees versus the 63 degrees where the angles are a little bit odd, you know, it's just not 60 or 45 or a number that we're used to. I could answer this is 270 pi. I could answer that in terms of pi or exactly. And then the arc length, everything is the same. It's 300 out of 360 is equal to, I want the arc length all the way around ACB over, in this case, it's because it's a distance around the circle, it's 2 times pi times r. 300 times 36 pi divided by 360. And you get 30 pi if you want an exact answer. Just you don't multiply the pi. You do 300 times 2 times 18 divided by 360. And you get 30 pi or 94.2. And that would be meters. Okay? Number 2, the area of a sector is 22 meters squared. So the area of the sector, that's our A that we call A sub S, right? The area of the sector, whatever variable you want to assign to it. The central angle associated with the sector is 45. So that we're going to use that for theta. Find the area of the circle. So I use my same formula. Theta over 360 is equal to the area of the sector over the total area. So theta was 45 out of 360 degrees. The area of the sector was 22 over the entire area. So I don't have to use pi r squared because all I'm asking for is find the area. So instead of putting pi r squared there, which I could put pi r squared there, solve for r, and then go find the area. But since pi r squared is the area of a circle, I'm just going to do it like this to simplify things a little bit. And we get that the area of the circle is 176 meters squared. That's the whole circle. You could also look at it like this, just kind of a side note of how you can kind of math through this. If it's 45 degrees, that's 360 out of 45. So if there are 360 degrees and I divide it into 45 chunks, 45 degree chunks, that means that there are 8. Well, the area of one of those pieces, so there are 8 pieces that are that size. So see, if I take that 176 and divide by 8, that's 22. So I could take 22 and multiply it by 8 and I get 176. That would be the whole circle. So because there are 8 pieces that are 45 degrees. So that's another way that you could logic through it if you wanted to. If that makes sense to you, it's just kind of helpful to think about it that way. All right, so we want the area of this segment. So now we need to do sectors and segments, because first thing we need to find is we need to find this sector. So the area of that sector, we have the area of the sector would be 90 degrees out of 360 degrees. So then what's the area of the sector, that orange piece, what's the area of the sector if the entire circle is pi times 12 squared? So you take, in this case, I want to leave them exact. So we would do 90 times 144 divided by 360, and we get that the area of the sector is 36 pi, because I want you to see what some answers could look like. So the area, if I asked for you to round, then you would just do 36 times pi. Okay, now I need the area of the triangle, and I need to take that area of the triangle. So the area of a triangle is base times height divided by 2. So if I take that, then the base and the height are both 12 and 12. So I have 12 times 12 divided by 2, 144 divided by 2 is 72. And so I took the big orange piece and I want to subtract the triangle so that all I'm left with is the blue piece. And so All I want is the blue piece. So I would take the 36 and subtract the 72, and we can leave our answer in terms of pi. So if you are asked to leave your answer in terms of pi, it will look like that. If you need your answer rounded, then you will type in 36 times pi minus 72, and actually that would give you approximately 8143. See, it's a little deceiving because 36 pi looks small, but it's actually 36 times 3. Oh, it's not. Sorry, made a mistake. I did times. It'd be 36. I thought that seemed big. 36 pi minus 72, not times, and it's 41.1. That makes a lot more sense. You should always look and see whether things make sense, and that would be square yards or yards squared. Look and see if things make sense. That was a really big number, especially for if you just estimate 36 times 3 for that 36 pi. That was way too big. All right, so when you get to 5, now we're going to get into some uglier finding the area of a triangle. So let's find the area of the sector first. I want the area of this entire piece. So the area of the sector is 120 degrees out of 360 degrees. And so what's the area of the sector if the entire area is pi times r squared? So 64 times 120 divided by 360. You get that the area of the sector is 64 pi over 3. If you math enter, it'll put it back into a calculator. If you put that into the calculator, it'll math enter it back into a fraction for you. If you're asked to leave it in terms of pi. Okay, so now here's the tricky part. We need the area of this triangle. So I'm going to take my triangle, and I have 120 here, and I need 8. Well, to find the area of a triangle, I have to have the height of the triangle. So I need the height of the triangle. Well, so we've got an angle there, so let's split that up. So I have 60 and 60. This is an isosceles triangle, right? And so now we have 30. Okay, so now we have to remember what we know. So remember with our 30, 60, 90s, it was x and then 2x and x root 3. So your x was across from the 30, your 2x was across from the 90 degrees, and your x root 3 was across from the 60. If you happen to, a 45, 45 you wouldn't need because that would be a right triangle anyway. So to do this then, I know that my hypotenuse is twice as long as my short leg, which means that this side has to be 4 and this side has to be 4 root 3. Now, this is a little tricky because this is also 4 root 3. So to find the area of the triangle, I need the base times the height divided by 2. So the area of the triangle is the base, 8 root 3. 4 root 3 plus 4 root 3 is 8 root 3, times the height, which is 4, divided by 2. Now, if you recognize it, you could do 4 times 4 root 3 and not divide by 2. You could do 4 times half the base, because it is half the base times the height. And so we get 16 root 3 if we leave our answer exact. So this is a potentially very ugly answer. It is 64 pi over 3 minus 16 root 3, which you can type in on your calculator. 64 pi divided by 3 minus 16 times the square root of 3. And you get 39.3. It's approximately 39.3, and that would be square inches. And then this last one, find the area of the segment if the central angle is 150 and the radius is 15. So we have our 15 right here. And I want the area of that segment. So let's find the area of the sector first. So it's 150 degrees out of 360 degrees. So what is the area of the sector if the entire area is pi r squared, a times 15 squared? So you do 150 times pi times 225. divided by 360. Now, I do know the direction that this is going to go, and I know that we need to round this one because I know we're going to end up using trig. So for this one, we'll round to the nearest tenth, okay? So the area of the sector then is 294.5 units squared. Now, here's the thing. I need to subtract that triangle. Okay, so here's my triangle. I need to subtract that triangle area. So I need the base and the height. I need those both. I don't have either one of those. So let me drop down this height. Now, I didn't draw a very good high isosceles triangle, but you can see that it is. Well, what I do is I bisect that 150, so that's 75. So let's call this y and let's call this x, and I need both of those pieces so that I can find the area. And because I have an angle and a side, that means I need to use trig. So don't forget SOHCAHTOA. Those are always fair game because we've already learned how to do them. So in order to find x, so I want to find x, I notice that it is opposite of the 75 and 15 is the hypotenuse. So that uses sine. So the sine of 75 is equal to the opposite side divided by the hypotenuse. So when I do that math, I want to multiply both sides by 15, and you get that x is equal to 14.5. So this is 14.5, and this is 14.5 because it's isosceles. Then we need y. Do the exact same thing, except that y is adjacent. So you would use adjacent and hypotenuse, so cosine. So the cosine of 75 is equal to x over 15. Multiply both sides by 15. And you get that y is 3.9. I should have called it y. Y is 3.9. So this is 3.9 right here. So now we've done all of that, but we still need to get the area of this triangle. The area of the triangle is 3.9 times 29, 14.5 plus 14.5. That's that whole base that we just found, divided by 2. So 3.9 times 29 divided by 2 is 56.55. Now you may be asked to carry these decimals out, so you'll want to go back in and use your previous answers. If it tells you not to round until the very end of the problem, you want to keep all of those decimals. And so now we take the area of our sector and we subtract the area of the triangle. So we take 294.5 and you subtract 56.55. And you get 237.95, which would round to 238.0. Now, just to give you an idea, when I worked the problem originally, when I was going through it, I used more decimal places and I got 238.2. So even just using a few more decimal places can cause your answer to be off a little bit. So be sure if the answer says to carry all of your decimals until the end of the problem, be sure that you do that. So in order to find a segment, we take the sector and subtract the triangle, which may mean we need to recall some things about our special rights and trig. And then to find the area of the sector in the first place, it's a portion of the original.